Hi friends, welcome to welcome to the lecture on time varying magnetic fields. Myself Satyanarayana Vanapalli. I am working as Associate Professor in the Department of Electrical and Electronics Engineering, Guntur Engineering College, Guntur. In this video, I am going to explain about time varying magnetic fields and Faraday's laws of electromagnetic induction and types of EMFs that are induced in real time. So, before going into the discussion, let us try to understand, or let me review the concept of time varying quantities. You know that whether it may be a current or voltage or magnitude or velocity or acceleration, whatever it may be, any physical quantity is said to be varying with respect to time if its magnitude is changing with respect to time. So, for example, here I am taking time on x-axis and magnitude on y-axis. Say I am taking flux phi, then if you observe this characteristic, the pi is, this line represents magnitude of phi. This line is parallel to time axis. So we can say that this quantity is having a constant magnitude. So if this magnitude is equal to some k, then we can write the value of pi as a function of time, which we can write it as pi of t is equal to k. So, if you observe the magnitude, this pi of t value at t is equal to 0 is equal to k, and say some t is equal to 10 and pi of t at t is equal to 10 is also equal to k. That means there is no change in value of pi of t. So I can say that this pi of t is time invariant quantity. It means the value of this pi of t not changing with respect to time. Now we take another example for a time varying quantity. Now we see how the relation between magnitude and a time will look like for a time varying quantity. Here I am taking time on x-axis, the same pi of t on y-axis, so that I am considering some different intervals of time. This time may be in seconds or milliseconds or something, any units of time, some units of time. Okay, so this pi of t, you suppose that is varying between two limits, a pi minimum and pi maximum. Some relation, okay, this variation may be a periodic variation or a periodic variation. But if you measure or if you write the value of pi of t at different instants of time, that means value of pi at t is equal to 0 is some pi minimum, and value of the same pi at time t is equal to 1 is pi maximum. Similarly, value of pi at a time t is equal to 2 is equal to pi minimum, and value of this pi at t is equal to 5 is equal to pi maximum. So if you observe this, the value of pi is not constant with respect to time. This value is varying. So this kind of quantities are said to be time varying quantities. So if this phi represents a magnetic field, then what happens if this kind of magnetic fields are linked with a conductor, or when a conductor is placed in such kind of magnetic fields, what happens, that we are going to know. So here the concept is simple. Here the concept is simple. What happens is, whenever any conductor is placed in a time varying magnetic field, then first we see how to produce a time varying magnetic field. This time varying magnetic field is produced either by moving the magnetic force or by moving the coil. You know that a current carrying conductor produces a magnetic field. According to Ampere's law, whenever electric current is made to pass through a conductor, then there establishes a magnetic field surrounding the conductor. So, based upon this phenomena, if you send a direct current, then the magnetic field that was produced surrounding the conductor is time invariant in nature. If a time varying current is sent through the conductor, then the magnetic field that was produced surrounding the conductor is time varying in nature. So, what I mean to say here is, a time varying magnetic field can be produced either by moving the coil or by changing the magnetic force. The magnetic force can be changed by changing the nature of the current that was sent through the coil. So, that means if I send a time varying current through the coil, which produces a time varying magnetic field, or if I send a time invariant current through the coil, it produces a time invariant magnetic field. So, if this time invariant current is sent through a coil, then it is possible for us to obtain a time varying magnetic field provided if the coil is moved or rotated. If time invariant current is made to pass through a coil, it produces a time invariant magnetic field. This time invariant magnetic field can be made as time varying magnetic field by means of rotating the conductor. Okay, please remember this point. This point is helpful in understanding the concept of production of electromagnetic field across the terminals of a coil. Okay, so now let us move to Faraday's law of electromagnetic induction. So, what this Faraday's law of electromagnetic induction says is a time varying field produces an electromagnetic force that may establish a current in a suitable closed circuit. It means if I took a coil so that a conductor is rotated inside a stationary magnetic field, this conductor is here. I took two cores over which two coils are wound, and these two coils are connected in series in such a way that one descending current through these coils, one core will act like a north pole, another core will act like a south pole, so that these two coils are separated by certain distance. As a result, there establishes a magnetic flux or magnetic field between the poles, so that the magnetic lines of force would be like this. So in the gap that was formed between these two coils, I started rotating a conductor in counterclockwise direction. So what happens if a conductor is rotated or moved inside this magnetic field? The flux that links with the conductor changes. So, as the flux linked with the conductor changes, there induces an EMF across the terminals of conductor. So, the EMF that was induced across the terminals of these conductors is equal to rate of change of flux linkages with respect to time. And the EMF thus induced or produced in the conductor will be in such a direction that opposes or that decreases the effect that was caused. So this EMF is produced because of this flux, so that this EMF will be in a direction opposite to the cause that was produced it. So this EMF will try to reduce the effect of magnetic flux. So to indicate this effect, here we introduce negative sign. So EMF is equal to the negative rate of change of flux linkages. EMF is equal to the negative rate of change of flux linkages. So that d pi by dt is the rate of change of flux, and if this conductor is provided with a closed path, then there establishes a current within the closed path. This is what Faraday's law says. So, the first point is a time-varying magnetic field produces an electromagnetic force that may establish a current in a suitable closed path. The second one is the electromagnetic force is merely a voltage that arises from conductors moving in magnetic field or from changing magnetic materials, so that the magnitude of this EMF is equal to minus d pi by dt. So, this magnetic flux is the flux that passes through any and every surface where perimeter is a closed path, and d pi by dt is the time rate of change of the magnetic flux. So, if there exist n number of filamentary conductors, so that the EMF that was induced inside the n number of filament conductors is nothing but EMF that was induced in the first conductor plus EMF that was induced in the second conductor plus EMF that was induced in the third conductor. Like this, if there exists n number of conductors, we will get n number of terms, so that by summing up all these n number of terms, this value is equal to minus n d pi by dt, where you know that in the previous slide we find out the amount of EMF induced in a single conductor. Like that, we have n number of conductors. This we can understand very easily. This is one conductor, another conductor is like this, and the third conductor is like this. If we join the end points of the conductors, then in this EMF induced is d pi by dt, negative sign. In the second conductor, EMF induced is minus d pi by dt. In the third conductor, EMF induced is minus d pi by dt. So all these three conductors are connected in series, so that the total induced EMF is equal to minus 3d pi by dt. If there exists n number of such conductors, this value is equal to n. So this n into d pi is known as flux linkages. N into d pi is known as flux linkages. But technically, this is known as EMF is known as voltage. Technically, EMF is known as voltage. So, according to the definition of voltage, V is equal to the closed integral E dot dl, where E is the electric field intensity. Therefore, we can write EMF is equal to closed integral E dot dl, which in turn equal to, for a single conductor, its value is equal to minus d pi by dt, or for a coil that is consisting of n number of turns in it, this value is equal to minus n into d pi by dt. Now, we know that the value of magnetic flux is nothing but the amount of flux that is radiating out of area. So, let ds be the differential area of the surface and B is the flux density. Then this flux is equal to integral over the surface B dot ds. B dot ds. So that if we substitute this value in the EMF equation, EMF is equal to integral closed integral E dot dl, that is equal to minus d pi by dt, where I can substitute s integral over s b dot ds. You know that these terms can be interchanged. Then, interchanging the integral and differential terms, this value is equal to integral over ds dou b by dou t dot ds. So, from these two terms, we can write it as integral closed integral over E dot dl is equal to integral over the surface dou b by dou t dot ds. So, with the help of Stokes' theorem, we can write it as integral closed integral E dot dl is equal to integral over the surface del cross E dot ds, which in turn equal to minus integral over the surface minus dou b by minus integral over the surface s dou b by dou t dot ds. If these two surfaces are equal, then we can write it as del cross E is equal to minus dou b by dou t. This equation is known as Maxwell's fourth equation. So, what this Maxwell's fourth equation says? You know that del cross E is equal to curl of E. So, the curl of E is equal to curl of electric field intensity is equal to curl of electric field intensity is equal to rate of change of flux density, change of magnetic flux density. Here it is not the rate of change, the negative rate of change of flux density. So that we can write it as del cross E is equal to minus 2B by 2T. This is called point form of Maxwell's fourth equation. Point form of Maxwell's fourth equation. So if you observe, Maxwell's fourth equation is nothing but Faraday's law. Maxwell's fourth equation is nothing but Faraday's law. What is Faraday's law? EMF is equal to minus dy by dt, which in turn equal to integral E dot dl. This in turn equal to integral del cross E dot ds. This in turn equal to minus dou b by integral over surfaces minus 2d by 2t dot ds. So this is Faraday's law, and by simplifying this in point form, this we can write it as del cross E is equal to minus dou b by dou t, and integral form, the same equation can be written as integral over the surface del cross E dot ds is equal to negative integral over the surface dou b by dou t dot ds. This form is called point form, and this form of representation is called integral form. Both the forms are correct. Okay, so let us move to next point. Now we see what are the types of EMFs that are induced inside a conductor. So, as you know that electric current is a result of flow of charges. It means whenever the charge is under movement, it constitutes electric current. So that you assume that a charged particle is moving inside a magnetic field with a velocity v, and let v be the magnetic field intensity. Let v be the magnetic field intensity, and the conductor is moving or rotated inside the magnetic field having magnetic flux density V. Then the force experienced by the conductor is equal to Q into V cross V. We know that the electric field intensity is force experienced by unit charge, which is equal to F by Q. Simplifying this equation, the electric field intensity E is equal to V cross V. Let this electric field intensity, we call it as motional electric field intensity, because this is called motional electric field intensity. Why? Because the conductor, this electric field intensity is named as motional electric field intensity. Motional electric field intensity. It is called motional electric field intensity because the charged particle is under motion. The charged particle is under motion. So that we can write the value of EMF induced inside the conductor or across the terminals of the conductor. EMF is equal to closed integral EM dot dl, which in turn equal to negative integral of V cross B dot dl. So, by applying splitting the integrals, we can write it as by splitting the integrals, we can write it as integral E dot dl is equal to minus integral over the surface dou B by dou T dot ds plus integral B cross B dot dl. So this equation constitutes of two kinds of EMFs induced in the conductor. This value dou B by dou T equal to 0 if B is constant. So that minus dou B by dou T over integral surfaces dot ds is known as statically induced EMF. It is called statically induced EMF because the conductor is stationary. There is no movement of conductor. And the second term, integral V cross B dot dl is known as dynamically induced EMF. It means if V is equal to 0, then V cross B is equal to 0. No EMF will get induced. So if V is not equal to 0, then V cross B not equal to 0, and this value will be equal to 0 provided it is, we are taking here the cross product of vectors velocity and flux density. This value may become 0 provided if V is in parallel with B. If V is not in parallel with B, then V cross B is not equal to 0. For all the values of V, it is not equal to 0. So under such conditions, this induced EMF is called dynamically induced EMF. Dynamically induced EMF. So, where this kind of EMFs are induced inside in real time. Statically induced EMF is known as transformer EMF, because in a transformer the conductors are stationary, but EMF will get induced in across the terminals of the transformer coils. And dynamically induced EMF is known as motional EMF. This motional EMF will get produced in a conductor when the conductors are in motion. So that is the reason why these EMFs are known as motional EMF. These motional EMFs are produced in rotating machines. So, in rotating machines, the EMF induced is dynamically inside the conductors, and in transformer, EMF induced is static in nature. So, we can conclude that the EMF that was induced inside a conductor is of two types. One is statically induced EMF, another one is dynamically induced EMF. Statically induced EMF will be induced in conductors that are stationary but subjected to time varying magnetic flux. And dynamically induced EMF will be induced in conductors if the magnetic field is stationary but the conductor is moving with velocity, and the angle at which the conductor is rotating should not be parallel to the magnetic field. Should not be parallel to the magnetic field. So, with this, I would like to conclude my explanation. Thank you for watching. Keep watching my channel for more topics and for more updates on electromagnetic fields. Thank you, and don't forget to subscribe my channel.